Imagine you're cruising down the highway.
Okay.
You're pushing maybe 80 miles an hour to pass a semi-truck, and you gently press the brake pedal to merge back into your lane. But in the 60 milliseconds it takes you to blink, the computer inside your electric vehicle's motor completely ignores your battery's safety limits.
Oh, wow.
Yeah. The motor decides it wants more power, the battery is screaming that it's melting down, and suddenly you are sitting on top of an unguided missile pulling just lethal amounts of electricity.
Right.
So today, we are doing a deep dive into the exact invisible digital warfare happening right under your floorboards.
It is, well, it's a terrifying scenario, honestly.
Yeah.
And the engineering required to prevent it from happening is arguably some of the most complex computational balancing taking place anywhere in the consumer world right now.
Absolutely. And we are exploring this because one of our listeners sent in a massive, incredibly detailed stack of technical specifications.
Yeah, they really did.
I mean, articles, research papers, their own engineering notes, custom tailored just for us to unpack. So the mission of today's deep dive is to demystify this highly technical, absolutely crucial automotive safety issue that engineers call a BMS limit conflict.
Specifically, we're looking at diagnostic trouble codes P087F and U0111L.
Right. And when I first opened the documents our listener shared, I assumed this was just, a standard glitch, like your infotainment screen freezing or your Bluetooth dropping out.
Yeah, but the automotive industry categorizes this completely differently than a frozen screen. A BMS limit conflict is what's called an ASIL D safety issue.
ASIL D.
Right. ASIL stands for Automotive Safety Integrity Level, and D is the absolute highest classification for risk.
Oh, wow.
Yeah. We are talking about failures that lead to life-threatening, unrecoverable situations. So uncommanded acceleration, a total loss of braking, or, a catastrophic battery fire.
So to understand why a car would suddenly go rogue like that, we have to establish the baseline of how an EV is actually supposed to work. In the specs our listener provided, the central character is the BMS, the battery management system. I kind of read the BMS as the overly cautious, risk-averse brain of the operation.
That is the perfect way to look at it, actually. The BMS is constantly monitoring the chemical and physical reality of the battery cells.
Like the temperature and stuff?
Exactly. Checking temperatures, the state of charge, overall health, internal resistance, all of it. And based on all that data, the BMS calculates two non-negotiable boundaries.
Okay.
The discharge power limit, or DPL, and the charge power limit, the CPL.
Okay, so the DPL is the brain saying, here is exactly how much power I can safely give you to accelerate without destroying the battery.
Right.
And the CPL is, here's how much power I can safely absorb back into the battery when you hit the regenerative brakes.
Exactly. And those limits aren't static. I mean, the BMS recalculates them dynamically, millisecond by millisecond.
Wow.
Yeah, and it sends those rules over the vehicle's communication network to the motor controllers, which, well, they act as the muscle.
Right, because the motor controllers just want to give the driver exactly the torque their foot just asked for on the pedal.
Yep, which sets up our core conflict.
Right. What happens when the dual motor inverter tries to execute a highly dynamic maneuver and the actual physical electrical power violently exceeds the safety limits the BMS just set?
That's the million-dollar question.
So before we get to the incredible safety nets engineers have built, the specs our listener provided outline 4 distinct root causes for why the muscle suddenly ignores the brain. And the first one essentially boils down to an invisible noise problem.
Right. Electromagnetic interference, or EMI.
Yeah, EMI.
The physics behind this EMI are just staggering. To achieve the massive performance and range we expect from modern EVs, the motor inverters use silicon carbide MOSFET switches.
Okay, let's break that down. A MOSFET is basically an electronic valve, right?
Exactly. It's a valve that turns the direct current from the battery into the alternating current the motor needs to actually spin. And silicon carbide allows these valves to handle far more power and switch on and off incredibly fast. I mean, we are talking about extreme voltage transients.
How extreme?
These switches can change states at a rate of 10 kilovolts per microsecond.
10,000 volts in a millionth of a second.
Yeah.
I can't even conceptualize that speed. I mean, does a physical switch moving that fast create some kind of digital radio wave or something?
It creates a violent electromagnetic shock wave, essentially. Because they switch so rapidly with such high voltage, they generate massive high-frequency noise.
And it doesn't stay contained.
No, not at all. Through phenomena known as parasitic capacitance and mutual inductance, this noise doesn't even need a wire to travel.
Oh, that's wild.
Yeah, the high frequencies essentially create temporary, unintended capacitors and inductors right out of the air and the metal housing.
So it just jumps.
Right, it allows this high voltage noise to jump the physical gap
Uh-huh.
and bleed directly into the car's low voltage communication lines.
I was trying to wrap my head around this jumping effect in the notes. It's like you are trying to give your friend vital life or death driving directions, but you are standing right next to a booming, distorted subwoofer at a heavy metal concert.
That's a great way to put it.
I mean, it doesn't matter how clearly you speak. The sheer acoustic violence just scrambles the message.
And in the digital realm, the car's communication network, which is the CNFD bus, gets hit with this electromagnetic subwoofer.
Right.
The data packets get corrupted. The system starts throwing cyclic redundancy check errors, which is basically the computer realizing the data is scrambled.
What does it do?
It just drops the frames entirely.
So the motor controller is sitting there waiting for its millisecond by millisecond update on the power limits, but it hears nothing but static.
Nothing.
What does it do then?
It assumes its last set of instructions are still valid. It latches on to these scale limits. Yeah. So the battery might be rapidly overheating and the BMS is screaming over the network, drop the power immediately. But the motor controller didn't hear it.
It's completely deaf to the warning.
Right. It keeps pulling massive current based on the old instructions, breaking right through the battery safety envelope.
Okay, so cause A is the deafening noise of EMI. Cause B, in our listeners' notes, takes us from digital noise to the physical reality of the motor literally bending.
Yes.
The documentation refers to this as inductance saturation and FOC model mismatch. I saw all these acronyms like LD, LQ, and I really need you to translate this one for me.
Well, let's strip away the acronyms and just look at the physical metal. When you push an EV to its absolute limits, you are pumping a massive amount of electrical current through the copper wire coils inside the motor.
Right, because that's what makes it go fast.
Exactly. This current creates a massive magnetic field, which is what spins the car's wheels. But the iron core of that motor can only hold so much magnetic flux.
So it has a physical limit.
Yeah, think of it like a sponge soaking up water.
Mm.
Eventually, the sponge is just
A
full.
deep magnetic saturation.
Exactly.
Yeah.
When you hit deep saturation, the iron literally cannot align any more of its magnetic domains. It's totally full.
Okay.
And at that exact moment, the physical properties of the motor radically change. Its inductance, which engineers measure as LD and LQ, experiences a severe, nonlinear drop.
So the metal stops behaving the way it normally behaves.
Yes, fundamentally.
But the software running the motor doesn't know that, right?
And that is the fatal mismatch. The software uses field-oriented control, or FOC. It relies on a mathematical model of how the motor usually behaves to calculate power limits.
Ah, I see.
So if the software's math models aren't dynamically updated to account for the fact that the physical iron has reached saturation, the math will calculate a completely safe power output.
So the software essentially hallucinates a safe scenario.
Pretty much, yeah.
It is looking at a theoretical model, saying, oh, everything is fine. Well, out in the real world, the physical hardware is melting down, and the actual direct current violently spikes past the limits.
Exactly. Relying purely on static theoretical models in high-stress environments is incredibly dangerous. The physical reality under extreme stress requires dynamic adjustments. Otherwise, the software will confidently drive the car right into a catastrophic failure.
Wow. Which brings us to cause C. We go from software ignoring physical reality to software ignoring other software. The listener specs call this priority inversion.
Right. Priority inversion is a classic software architecture trap, and it really comes down to how microprocessors juggle multiple tasks.
Okay.
The algorithms keeping the EV's motor spinning smoothly have to run incredibly fast. They usually operate on a high-priority, ultra-fast loop that triggers every 100 microseconds.
Right, because if the timing of those massive magnetic fields is off by a fraction of a millisecond, the motor probably tears itself apart.
Absolutely. Yeah. Now, receiving the messages from the BMS with the new safety limits is also vital, obviously. But historically, that's handled by a slower, lower priority task, maybe updating every 10 milliseconds.
Because it doesn't need to be as instantaneous as the physical spinning.
Exactly. And under normal conditions, the processor handles both easily. But if the system suddenly gets hit with a high computational load, say a burst of network traffic or a really complex traction control event, the processor gets overwhelmed.
It gets tunnel vision.
It does.
Yeah.
It drops the lower priority tasks to ensure the high priority tasks survive. The CPU gets so bogged down keeping the ultra-fast motor loop running that it completely ignores the slower task trying to unpack the new battery limit.
So the fast loop runs blind.
Right. It runs blind using old data.
Yeah.
And again, you trigger a critical limit conflict because the motor is prioritizing spinning over, listening to the command to stop.
It's wild how quickly things break down. Okay, cause D is where this deep dive gets, honestly, delightfully mundane.
Oh, yeah.
Because we've covered invisible electromagnetic shock waves, magnetic saturation of iron cores, and priority inversions in microprocessors. And then I get to the fourth cause in our listeners' notes, and it's literally just about a bolt.
Just a humble metal bolt, specifically bus bar impedance wear.
Okay, what is a bus bar?
The high voltage power from the battery flows to the motor controllers through thick, solid metal plates called bus bars. These plates are bolted together to create a continuous electrical path.
But the notes specifically mention a missing phosphate surface coating on these bolts. I mean, why does a microscopic chemical coating on a bolt matter to a supercomputer?
Because without that specific phosphate coating, the friction on the threads of the bolt is uneven.
Oh, I see.
When the robotic arm at the factory torques that bolt down, the machine might measure the correct twisting force. But because the friction is wrong, it doesn't achieve the required axial clamping force.
So the plates aren't squeezed together tightly enough, and cars vibrate constantly. You hit a pothole, the metal expands and contracts from the heat of the electricity.
Yeah, and over time, that slightly loose bolt backs out just a fraction of a millimeter. You now have a micro gap between the massive metal plates.
Just a tiny gap.
But when hundreds of amps of current try to push through that gap, you get intense localized heat, and you get a measurable voltage drop across that joint.
So how does a voltage drop trick the software into a catastrophic failure?
Well, the motor controller has local sensors measuring the voltage at its end of the bus bar to calculate how much power it is using.
Right.
Because of the loose bolt, it reads an artificially low voltage. The controller does the math and says, oh, the voltage is low, so we are pulling a safe amount of power.
But it's lying to itself.
Right, because the battery sitting on the other side of that loose bolt is seeing the true, much higher voltage and the massive current draw.
So the motor controller's math is wrong simply because its sensors are being starved by a single loose bolt.
Yes.
The battery knows they're pulling too much power, it triggers a massive alarm. But the motor controller thinks everything is totally fine. It's the ultimate butterfly effect.
It really is.
A microscopic lack of friction on a single thread of a bolt leads to an ASIL D life-threatening software conflict.
It perfectly illustrates why automotive engineering cannot separate the digital from the physical. I mean, software is only as good as the hardware delivering its reality.
That is profound. Okay, so knowing all of this, knowing that electromagnetic noise, magnetic illusions, distracted processors, and uncoded bolts can all cause the system to fail, how does the car actually survive?
Wow.
When I look at the safety net section of our listeners' sources, the entire architecture revolves around one incredibly stressful metric, the FTTI.
The fault-tolerant time interval. For an ASIL D system, automotive standards mandate an FTTI of 60 milliseconds or less.
60 milliseconds. A human eye blink takes about 300 milliseconds.
Yeah, so the system has 1/5 of a blink.
That is insane.
That is the maximum time allowed from the exact moment a fault physically occurs for the computer to detect it, verify it isn't a false alarm, and transition the entire vehicle into a safe state.
And if it's too slow?
If it takes 61 milliseconds, the engineering fails, and the occupants are in real danger.
So how does it detect the failure that fast, especially if the root causes we just discussed involve the sensors themselves getting bad data, like with the bolt?
It uses power plausibility diagnostics.
Yeah.
The system is designed to never trust a single source of truth.
Okay, cross-checking.
Exactly. It continuously calculates the actual physical direct current coming in from the battery and simultaneously calculates the alternating current being consumed by the magnetic fields in the motor.
Right.
And it cross-checks them against the dynamic limits coming over the network. If anything diverges, a timer starts immediately.
In the notes, it outlines a two-stage warning system. Level 1 seems to be a soft conflict. If the power exceeds the battery's limits by more than 5% and it stays there for 10 milliseconds, the system flags a light fault.
Right. It basically says, something is drifting, let's keep an eye on it.
But the level 2 fatal warning is where the FTTI kicks in. If the actual power exceeds the limits by more than 15% for just 5 milliseconds, the software essentially categorizes it as a deadly, unrecoverable conflict.
And at that point, software control is completely abandoned.
It just gives up.
Well, hardware safety systems violently take over.
The hardware takeover is fascinating because it relies on this doer-checker dual-core brain. When I was reading the specs, I honestly struggled to visualize this. It is a single processor chip, but it has two separate brains inside it.
Yeah, a lockstep architecture.
I was trying to picture an analogy for this. It is almost like having a race car driver and a driving instructor sitting in the exact same car.
That analogy works perfectly, actually. The main core is your race car driver, the doer. The doer is executing the highly complex, ultra-fast mathematical racing lines, calculating torque vectors microsecond by microsecond.
Going as fast as possible.
Right. But the checker core, the driving instructor, isn't looking at the complex math.
Why not?
Because if there is a fundamental bug in the complex math, both cores would get the same wrong answer.
Oh, that makes sense.
So instead, the checker uses simplified, fundamental physics models. To use your analogy, the driving instructor isn't looking at the telemetry data on a screen. They are just looking out the window at the concrete wall.
Right.
They're using basic conservation of stator flux to estimate what the motor should be doing.
And if the race car driver suddenly steers toward the wall...
The driving instructor doesn't argue. They just slam the secondary brake pedal.
Wow.
If the checker calculates that the doer's output will cause a massive power spike, it bypasses the main processor entirely.
Just cuts it out of the loop?
Completely. It sends a distress signal to a separate, physically isolated chip called the System Basis Chip, or SBC, which cuts power to the motor in less than 100 microseconds.
Okay, I have to push back on this, though.
Go for it.
This sounds great in a laboratory, but if I am driving 80 miles an hour down the highway, and the doer and the checker disagree, and this isolated chip just shuts the motor off in less than a millisecond, isn't that incredibly dangerous?
How so?
Well, if my wheels suddenly lock up at highway speeds because the motor just died, I am going to crash.
And you've hit on the exact reason why EV safety engineering is so incredibly difficult. You cannot simply cut the power at high speed.
Because of the momentum.
Because a spinning electric motor is also a massive generator.
Oh, right.
If you physically open the circuits to cut the power while the motor is spinning at 12,000 RPM, the motor will instantly generate a massive amount of uncontrolled voltage. It's known as back electromotive force.
Back EMF.
Yes. It will pump that violent voltage backward into the battery, overcharging it in milliseconds and potentially causing a catastrophic fire.
Right, because it's just a giant permanent magnet spinning inside coils of copper wire. It doesn't care if the computer is turned off. It's going to make electricity if it's spinning.
Exactly.
So how do they stop it safely in under 60 milliseconds without blowing up the battery?
Through adaptive safety responses. Specifically a technique called this stepwise active short circuit.
Stepwise active short circuit.
Right. If the system detects a fatal fault while the motor is spinning at high speeds, generally over 7,200 RPM, instead of turning the motor off, it intentionally short-circuits the motor's own internal windings.
It short circuits itself on purpose.
On purpose.
That sounds like hitting the self-destruct button.
Well, it acts as a controlled self-destruct of the kinetic energy, not the car itself. By short-circuiting the three electrical phases of the motor together in two incredibly fast steps, it completely isolates the motor from the battery.
Okay.
All that kinetic and magnetic energy is suddenly trapped inside the motor itself. The spinning motor turns into a giant self-contained heater.
Oh, wow.
The kinetic energy is converted directly into heat within the heavy copper stator windings.
And is absolutely brilliant. It forces the motor to eat its own momentum.
It successfully clamps the direct current voltage to a safe level, which is mandated to stay under 720 volts. And that completely protects the battery from that explosive overcharge.
And what happens to the driver?
Because the energy is dissipated as heat over a few seconds rather than an abrupt mechanical lockup, the driver experiences a smooth, relatively safe coast down.
That's a huge relief.
Yeah. Now, if this failure happens at a low speed, say under 2,000 RPM, the generated back voltage isn't high enough to threaten the battery. So the system simply executes an active open circuit, essentially putting the car in neutral and letting it freewheel.
So within a window of 60 milliseconds, the computer realizes it has failed, evaluates the physical speed and momentum of the vehicle, and chooses the safest possible method to kill its own propulsion.
Exactly.
The 60 millisecond safety net is a marvel. But obviously you don't want to be constantly short-circuiting your car and motors on the highway.
No, definitely not.
We need to look at how engineers design and build out these flaws from day one so the net is rarely needed. The listener's specs break this down into DFMEA, design failure mode and effects analysis, and PFMEA, the manufacturing side.
Let's start with the design fixes.
Yeah, how do they stop the root causes?
Let's look at cause C first. The priority inversion, where the processor gets distracted. The design fix is forcing absolute draconian synchronization.
Draconian, really?
Engineers mandate that the main microprocessor, the external communication chips, and the isolation decoders must all share a single, ultra-precise hardware clock source on the circuit board.
Oh, so they can't keep their own time. They all march to the exact same external drumbeat.
Right. They synchronize the clock phases so tightly that the error margin between chips is less than 0.5 degrees.
Wow.
This hardware-enforced synchronization ensures that no data packet gets dropped or delayed simply because one chip was a fraction of a microsecond out of step with another when the load spiked.
That solves the distracted processor. What about the noise? Cause A, that screaming loud electromagnetic interference from the silicon carbide switches. How do you stop a digital shockwave?
You build digital fortresses.
I like the sound of that.
In the design phase, engineers specify high-end isolation chips with a common mode transient immunity, or CMTI, greater than 100 kilovolts per microsecond.
So they can withstand massive interference.
Yeah, they build physical, highly resistant barriers on the circuit board that the noise simply cannot penetrate. Furthermore, they install common mode chokes on the communication lines themselves.
I saw the term choke in the specs, but I didn't fully understand it. How does a choke work?
A choke is essentially a specialized inductor, a small coil of wire. Its physical properties allow low-frequency, intended data signals to pass through unimpeded.
Okay, the good data gets through.
But when high-frequency noise hits it, the choke acts like a massive wall of resistance, heavily attenuating or choking the interference.
That's the name.
Right. The automotive specs require these chokes to block at least 40 decibels of high-frequency noise. It is quite literally putting noise-canceling headphones on the communication chips.
Okay, I love that analogy. Now, what about cause D? The loose bolt causing resistance, which generates heat, which throws off the local sensors.
Well, you can't always stop the heat, so you have to make the sensors immune to it. This requires mandating thermal-proof components. To ensure the voltage sensors don't drift as the metal around them heats up, the design strictly mandates the use of Class 1 C0G ceramic capacitors and ultra-precise thin-film resistors.
Why is a Class 1 C0G ceramic capacitor the gold standard here over, just a standard component?
It comes down to their molecular structure. Unlike standard capacitors that use materials prone to shifting under thermal stress, C0G capacitors use a specific dielectric material that does not change its electrical capacitance regardless of extreme temperature swings.
I just don't care about the heat.
Exactly. And the thin film resistors, paired with them, have a thermal drift of less than 25 parts per million per degree Celsius.
So they are practically inert to heat?
They kill the fake sensor readings right at the source. If the voltage sensor registers a drop, the computer knows it's a real physical event, not just a temperature artifact.
Brilliant. And finally, cause B. The magnetic illusion where the iron core gets saturated, the inductance drops, and the software model basically hallucinates.
Yes, the sponge gets full.
Right. How do they design a static math model to understand bending physics?
Through adaptive math. The engineers strip out those static theoretical inductance numbers and replace them with dynamic two-dimensional lookup tables, or 2D LUTs.
So instead of a single number, the software has a massive topological map of exactly how the physics will warp under every possible combination of torque, speed, and temperature.
That's it, exactly. It provides real-time feed-forward compensation, but they go even further than that.
Whoa.
They run parallel background algorithms, like recursive least squares, that constantly recalculate and relearn the physical electrical resistance of the motor's stator as it heats up to 150 degrees Celsius.
Constantly relearning.
Yeah, the software is continuously analyzing its own physical body, updating its math based on the real-time state of the motor.
So the digital brain is constantly aware of exactly what shape the physical muscle is in. That covers the design side, the digital fortress. But as I read further into the listener's sources, I realized that design is just theory. It is one thing to design the perfect, fail-safe circuit board on a computer. It's another thing entirely to manufacture 10,000 of them perfectly on a factory line.
Exactly.
I mean, if a factory robot has a tiny calibration error during assembly, does all that brilliant math even matter?
It doesn't matter at all. A microscopic manufacturing defect in a high-voltage system instantly becomes a lethal failure out on the road.
Wow.
And this is where PFMEA, process failure mode and effects analysis, takes over. Let's look at how they actually build the circuit boards, the brains of the operation.
Okay.
When the microprocessors and those high-end isolation chips are soldered onto the board, there is always a risk of microscopic air bubbles, called voids, forming inside the melted solder joints.
And I imagine if you have an air bubble trapped in a joint and the car vibrates over a pothole 5 years later, that bubble causes the joint to crack.
A cracked joint means a broken connection, which means a total loss of safety communication.
Which is an ASIL D failure.
Yes. So to prevent this, the factory line employs X-ray vision. Literally. Every single critical circuit board must pass through a 3D automated X-ray inspection or an ultrasonic scanning acoustic microscope. They don't just look at the surface, they peer deep inside the solid metal of the solder joints.
What kind of tolerances are they looking for inside the metal? I mean, how small of a bubble is too small?
The limits are brutal. The total voiding rate on any critical connection pad cannot exceed 5% of the total volume.
5% total.
And a single isolated void cannot be larger than 1% of the pad area.
Wow. And what happens if it fails?
If a board fails this invisible inspection, the system physically locks the assembly line.
Just shuts it down.
It will not allow that specific board to move to the next station. It completely removes human judgment or the temptation to, pass it through just this once.
It just shuts the line down. That is rigorous. Okay, what about my favorite problem, the loose bolt without the phosphate coating? How does the factory guarantee every single bolt on the bus bars is perfect?
They utilize what you could call the ultimate screwdriver.
Sounds intense.
The assembly line stations use highly advanced servo screwdrivers. These aren't your typical garage torque wrenches that just click when they hit a certain pressure.
Right.
These robotic drivers dynamically monitor the precise torque angle curve of every single bolt as it's being driven into the metal.
So it's actively measuring how much force it takes to turn the bolt every fraction of a degree, basically drawing a graph in real time.
Exactly. And because engineers know the specific friction profile of a bolt with the phosphate coating, the system can instantly detect if a bare, uncoated bolt accidentally slipped into the parts bin.
Just by feeling the resistance.
By perfectly matching the torque angle curve, they guarantee the clamping force is flawless, ensuring the electrical resistance across that joint stays under 5 microohms.
5 microohms. That is practically zero resistance. It is as close to a continuous piece of metal as you can get.
It has to be. And finally, even with the X-rays and the servo screwdrivers, before any completed motor drive unit is allowed to leave the factory, it faces the EOL, end-of-line, shock test.
This isn't just a gentle spin to make sure the bearings aren't squeaking, is it?
No, not at all.
How hard do they push a brand new motor before it even sees a car?
They bolt the motor onto a massive test rig and command 100% maximum torque, full red line power.
Right out of the gate.
While the motor is screaming at maximum physical load, the test machine suddenly injects a fake CAN bus signal that instantly drops the BMS power limit down to 20%.
A simulated catastrophic limit conflict right on the factory floor.
Yes. The newly built unit must instantly recognize the new severe limit and smoothly ramp down the immense physical power to fit inside that tiny 20% window within 10 milliseconds.
And if it doesn't?
If the response is sluggish, or if the power spikes during the transition, the manufacturing execution system automatically rejects the unit. It will absolutely refuse to print a shipping label.
The gauntlet is thrown down before the motor is ever allowed to meet a chassis. Okay, so if we zoom out based on our listeners' documents, you've designed this system flawlessly with synchronized clocks, noise chokes, and adaptive math mapping physical reality.
Right.
You've manufactured it perfectly with X-ray vision and micro-ohm torque curves. But now you have to prove it can actually survive the brutal reality of the open road.
That's the real test.
That brings us to our final section. DVP&R, or Design Verification Plan and Report. This is the ultimate torture test.
This is where pristine engineering theory meets absolute physical brutality. You have to definitively prove that all these intricate defenses actually work when everything goes wrong simultaneously.
Take me through the first torture test they run.
It goes back to that high-load EMI injection. Engineers place the entire motor controller assembly into an environmental isolation chamber. They spin the motor up to an agonizing 12,000 RPM under incredibly heavy load.
Just maximum physical stress.
Then they deliberately blast the chamber with maximum frequency electromagnetic interference, simulating the absolute worst-case switching noise from the silicon carbide valves.
Just deafening it with noise.
And while they're deafening the system with ambient noise, they use a testing device hooked directly into the wiring to intentionally inject dropped frames and CRC errors into the communication network.
They are actively hacking their own system, trying to break the communication lines while the motor is redlining.
Yep.
What defines a pass or fail here?
The passing criteria is strictly binary. The software's filtering and debouncing mechanisms must work perfectly. It cannot falsely trigger a shutdown.
So it can't just panic and lose power because of a minor glitch.
Right. However, if the engineers sustain the communication blackout for more than 100 milliseconds, proving the connection is truly dead, the system must smoothly ramp down the motor torque at a safe, controlled rate of 500 newton meters per second.
No violent jerks, no massive current overshoots, just a safe, controlled surrender.
It has to fail gracefully under heavy fire.
Wow.
The next test proves physical endurance. The 500-hour shake and bake.
I read that heading and thought it sounded like a terrible cooking show.
It is significantly worse for the electronics. They subject the entire unit to brutal, random, 3-axis vibration. The specification requires a root mean square acceleration, GROMS, of greater than 35.
So it is violently, randomly shaking in every direction.
While running high voltage power through it. And simultaneously, the chamber cycles the ambient temperature from negative 40 degrees Celsius all the way up to a boiling positive 125 degrees Celsius.
Oh my God.
And they do this continuously without stopping for over 500 hours.
Over 20 days of continuous violent shaking, freezing, and boiling. How can you even measure success after that much abuse? I feel like anything would be destroyed.
After 500 hours, they measure the electrical resistance of the microprocessor in those isolated communication chip solder joints. The electrical resistance cannot have shifted by more than 1.2 million.
That is such a tiny margin.
Furthermore, looking at the data logs during the entire 500 hours, there cannot be a single control signal or sensor dropout that lasts longer than 1 single microsecond.
Wait. 1 microsecond of dropped data in 500 hours of physical torture is considered a failure.
A total failure.
That is just, I can't even process that.
And they don't just trust the data logs. After the test, they perform destructive physical analysis. They literally cut the circuit boards open and put them under high-powered microscopes to visually confirm that there are 0 fatigue microcracks forming in the solder.
That level of paranoia is astounding, but the last test listed in the specs sounds like the climax of a sci-fi movie.
The hell load dump.
Right. I know HL stands for hardware in the loop, but what does this test actually do?
This is the ultimate simulated disaster. They connect the actual physical hardware brain, the controller, to a massive, ultra-fast FPGA supercomputer that simulates the physics of the entire rest of the car in real time.
So the brain thinks it's in a real car.
Exactly. They spin the simulated motor to 12,000 RPM at full load.
And then what goes wrong?
Everything goes wrong. They trigger a worst-case scenario. The supercomputer simulates a sudden, massive drop in the battery's power limit, simulating a catastrophic chemical crisis.
Okay.
At the exact same millisecond, they simulate a physical failure where the high-voltage relays violently cut open. A full load dump.
So the motor is screaming at maximum power, the battery is screaming for it to stop, and the physical connection between them is violently severed.
It is the ultimate catastrophic limit conflict, and the requirements for the hardware to pass are absolute.
Let's hear.
The safety system must definitively detect this complex failure in under that 60 millisecond window. It must instantly trigger the stepwise active short circuit we discussed earlier, shorting its own windings.
Trapping all that violent energy inside the motor as heat.
Yes. It must clamp the transient voltage spike so it never exceeds 720 volts, protecting the simulated battery from frying. It has to manage the demagnetization current so it stays under 550 amps.
Okay, that's a lot to manage in milliseconds.
And crucially, it has to orchestrate all of this violent electrical mitigation so smoothly that the physical torque fluctuation felt on the wheels is less than 5 Newton meters.
Less than 5 Newton meters.
Right.
So let me get this straight. The entire electrical system is having a catastrophic high-voltage meltdown. The computers are intentionally short-circuiting the motors in milliseconds to trap the energy.
Right.
And the person sitting in the driver's seat
Feels nothing more than a smooth, safe deceleration. They don't experience a violent jerk. They might coast to the shoulder of the highway without ever knowing how incredibly close they just came to a lethal, fiery failure.
That is just incredible engineering. It's almost poetic.
It is.
Okay, if we step back and look at the broader implications of everything our listener shared with us today. We started this deep dive talking about an invisible tug of war,
Yeah.
a tiny bit of magnetic illusion, a single dropped data packet from a silicon carbide switch, or literally a single uncoded bolt. Any one of those mundane things can tell an EV motor to ignore the battery and pull lethal amounts of power.
And to counter that immense fragility, we saw an architecture that forces microprocessors to march to a synchronized clock, checks its own math in dual-core lockstep, makes life-or-death decisions in a fifth of a human blink, and is perfectly willing to intentionally short-circuit its own motors to save the battery.
We saw assembly lines equipped with 3D X-ray vision locking down if a solder void is 1% too large, and torture tests that literally shake, bake, and freeze electronics for 20 straight days looking for a single microsecond flaw.
Going through these specifications really reframes what a car actually is today. When you press the accelerator in a modern EV, you are no longer just engaging a battery and a motor through a cable.
Not at all.
You are commanding a massive, real-time supercomputer that is constantly negotiating physical limits, constantly checking its own sanity, and is fully prepared to sacrifice its own momentum to protect your life.
It is breathtaking.
Yeah.
And it actually brings me to a final thought I want to leave everyone with, which was buried at the very end of the source material our listener provided.
The simulation tool.
Yes. There is a technical note offering the use of a Python simulation tool to model what they call electrothermal dynamic coupling during these violent power reflows.
Which is fascinating.
Basically, engineers now have to use highly advanced physics simulators just to map out exactly how much safety margin they have before the physical metals melt.
It has become an absolute necessity. The interactions between software, electromagnetism, and thermal dynamics are so complex that human intuition simply isn't enough anymore. You need supercomputers to simulate the safety systems of the supercomputers we are putting inside the cars.
And that is exactly what I want our listeners to mull over today. Right now, we are looking at passenger cars, which thankfully roll on the ground.
Yes, thank
But
you.
standard EVs already require this mind-bending level of complex real-time physical and thermal simulation just to design a fail-safe that works in 60 milliseconds. What is it going to take to secure the next generation of transportation?
It's a huge question.
Think about the electric vertical takeoff aircraft, the flying EVs that companies are building and testing right now, or fully AI-driven autonomous semi-trucks hauling 80,000 pounds of cargo down a mountain pass.
The stakes are infinitely higher.
In those scenarios, gravity and massive payloads mean your safety margins are even slimmer. If a flying car has a 60 millisecond BMS limit conflict, it can't just execute an active open circuit and freewheel to a stop on the shoulder.
No, it falls out of the sky.
Exactly. If this exhaustive, paranoid level of engineering is what it takes to keep a sedan safe on the highway, the architecture required for the next decade of autonomous and airborne EVs is going to have to be practically flawless. It makes you wonder, when gravity is involved, is 60 milliseconds going to be fast enough?